Alright, for some of you who are looking for another lesson on inclined planes, I've decided to try to make a lesson for you. I'm currently sitting in the Minneapolis airport waiting for my connecting flight, so you might be hearing some background noise and people walking by. I'm also trying a new program, so bear with me if all of a sudden things aren't working out, but I'm going to try to explain things as best I can. With inclined planes, we have the idea of a ramp. That's really what it's about. And that there happens to be some object on that ramp, on that incline. For now, we're going to be leaving out friction. So hopefully what people can recognize is that this object is going to want to naturally slide down this way, exactly parallel to the incline. It's not going to want to rise up or rise in or go dig into the incline. So what we're really thinking about is that this is our new surface. This is our new ground. It just happens to be on an incline and not perfectly flat like we're used to, like this one. Of course, there is an angle here, and often we'll have a situation where the angle is given to us. So most of the time we think of the angle as being like that, and that's going to help us out later. Now, normally, we think of force as being perfectly straight up and down, and perfectly sideways like this. And then often, those kinds of situations are helpful. And if we happen to get forces where we have them going one direction and the other direction, we can just simply add or subtract them. Or if both of them are going up, we can add them. And if one's going up and one's going down, we subtract them, or one's going right, one's going left, we subtract them, that kind of idea. But if we have forces where one is going sideways and one is going up, then all of a sudden we have this hypotenuse idea. So it's like that we have normally, or if we have one force like this and another force like this, we then figure out the net force doing that. Now, while we know how to do this, we've been doing this kind of work before. If we can get a way of not doing this and just simply adding vectors that are in the same direction and getting the total like this, that math is way easier. You're just simply adding the values. Or if you happen to have vectors where they're going opposite, and then we have the idea that there is this net force where it's the subtraction of these two here to give us the net force of this. These two situations are way easier to deal with than this, even though we know how to deal with this. All right, I'm going to see if I can erase some stuff here now. Eraser. All right. Oh, maybe it's not letting me erase. I thought that was an eraser. All right, let's see if I can get rid of a bunch of stuff here. No, doesn't seem to be. Okay, anyway, I'll keep going. If we draw free body diagrams, we've got the idea that we've got a force like this, which we call Fg. And we also have a normal force. But what we need to remember here is that the normal force is always perpendicular to this. And perpendicular means 90 degrees. So we have a force normal that looks like that. I'm not necessarily sure how big it is, but hopefully we can understand already that this normal force is likely going to be smaller. This normal force is likely going to be smaller than Fg. The only time it's the same when we have just an object resting on a surface is if it's on a flat surface like this. Now, before, when I was talking about that this is more problematic than this, these two forces are not at right angles to each other. So we can't even use this mathematics, because this is assuming a right angle triangle right in here. This is not 90 degrees. It's something else. So what we do is instead of thinking vertical to be this way and horizontal to be that way, what we consider is horizontally to be parallel with the surface and vertical to be perpendicular with the surface. So now all of a sudden, it's like we have our graph not going sideways and up and down. We have our graph going this way and that way. So it's as if what I've done is I've made a brand new coordinate system that looks like this. And this is my x direction, and that's my y direction. Now all of a sudden, the normal force is pointing straight up in the y direction. And it's Fg that's now on some strange angle. Now what we've done in the past is if we've had a force on an angle, we then break it up into components. Sort of the reverse of this. In the past, if we've had a force that's on an angle, we then break it up into its horizontal component and its vertical component. Oops, that should be dotted. If we had a force on an angle, we broke it up into horizontal component and into a vertical component. That is what we're going to do with this force here. But in this case, our vertical and horizontal look different. This is our vertical. This is our horizontal. We're going to call this one FGY and this one FGX. And right in here is a 90-degree triangle. So that means that we can actually use this idea or this idea because we have a 90-degree triangle. If we happen to know the hypotenuse, we can use trigonometry to figure out these two sides provided that we have another angle. So that means we do need another angle. Now, I'm not interested if you know how the geometry works, but all I can tell you is that whatever this angle is going to be the same as this angle in here. Always. Every single time. I cannot think of a single case where it's different. So that means that this angle in here is exactly the same angle as this one. These two are the same. So now what I've got is a right angle triangle that looks like this. This is the hypotenuse. This happens to be the opposite side to the angle. This happens to be the adjacent side to the angle. So what we've got is a brand new triangle that kind of looks like this. Now, provided that we know the mass here, we can figure out what this is. Because we do know that Fg is equal to mg. If I know the mass of this, I just multiply it by gravity, and I can figure out how much this is. I'm figuring out the weight. And so if I know what this is and this angle, I can use trigonometry to figure out Fgx and Fgy. Now the neat thing about this is that Fgy and Fn are exactly opposite to each other. Now I haven't drawn this to scale, but this force and this force are going to cancel each other out. Because as this box begins to slide down, it doesn't come off of the incline, it doesn't dig into the incline. So that means that those forces in the y direction must cancel. These two cancel out. And so now what happens is that all that's left over is Fgx. Remember that we've taken this force and we've pretended that it's broken up into this one and this one. So before we had 2 forces, and now what I'm pretending is that I have 1, 2, 3 forces. So if this one and this one cancel, then all I got is Fgx. And if that's the only force, then that has to be the net force. So let's see if we can figure out a calculative example now. So here I've got an example set up already. I've got a 5 kilogram box on a 20-degree incline. And of course, we're assuming that there's no friction. So if I do a free body diagram, I've got Fg, I've got Fn, And then I break up FG into FGY and FGX. So right now, let's just try to figure out what a bunch of different things are. I'm going to just try to figure out what FG is. I'm going to try to figure out what FGX is. I'm going to try to figure out what FGY is, what FN is. I'm going to try to figure out the net force. And ultimately, I'm going to try to figure out what the acceleration is. All right, let's see if I can do this with the math equation editor here. I've got that. All right. F, G, FG is equal to MG. Okay, FG equals MG. And so then, that's not what I want. And I move this elsewhere. Okay, hold on. We've got F, G. Let me just move this over here. FG equals, now in this case the mass is 5. So I want to open bracket here. How do I do open bracket? Nope. Alright, well, we'll do it this way. 5 times 9.8. I'll do it that way. Okay? And then when I do that, I'm going to equal 49 newtons. Alright? So that happens to be FG. Now I'm going to try to figure out what FGY is. Remember that this angle in here is 20 degrees, and this angle of 20 degrees is the adjacent side to this. So if I remember that the cos of the angle is equal to just a second, here we are, is equal to, in this case, the adjacent divided by the hypotenuse. And in our case, the adjacent side is FGY. So FGY, and the hypotenuse is FG. If I want to figure out what FGY is, all I have to do is multiply this side and this side by FG, and then I'll get FGY. So now my equation is going to look like this. FGY equals FG cos, and in this case, it is 20 degrees. And using my calculator, oh, sorry, I'll have to add one more thing here. What will happen then is that FGY will equal, FG was 49 times the cos of 20. And when I use my calculator, I get 46.0, so 46.0. All right, good.
Welcome to Delta
Now-
Flight 2113 to Kansas City. This flight is in cooperation with our coach here.
So because we know that this one and this one are equal and opposite, then all I need to say
prior to departure. Please watch the gate information
is
screens
that
overhead for additional flight information. As
F
always, thank you for choosing Delta.
N equals FGY, which is going to equal R46. That's all I really need to say. Yeah, it's technically in the opposite direction, but we can understand that. So I've got two answers already, FGY and FN. Now if I want to figure out FGX, it happens to be the opposite side of this angle, so I'm going to use sine. So I really am doing this again. So let me add another one here. We've got the definition of cos of the angle is equal to opposite. Sorry, we don't want cos. My mistake. Hold on. We want sine. We want sine of the angle is equal to opposite over hypotenuse, which is then equal to, in this case, FGX divided by FG. So hopefully you can see that this structure and this structure look very similar. The only thing is different is really sine and cos, and which ones happen to fit it in there. So to get from here to here, I took FG and multiplied it to the other side. That's what I'm going to do here. I'm going to take FG and multiply it to the other side. So I'm going to get FGX is equal to FG sine of the angle. Oop, not that one. Sine of the angle. There we go. And I do know, of course, that the angle here is still 20, so I'd put in 20 there like I did over here, just forgot. So if I put this in, and now I'm going to have FGX is equal to 49 sine of 20, which is equal to 16.8 newtons. There we go. Now because these ones cancel out over here, really all of this is gone. All I'm left with is the FGX. Then I know that Fnet is equal to FGX, because Fnet's just adding them all together, and all I have is this to add. So I then have Fnet is equal to FGX, which is going to be equal to our 16.8. So now that I've got what the net force is right here, now what I can do is to figure out the acceleration using F net equals ma. F net equals ma, and in this case, this is going to equal our mass of 5, and I'm going to multiply that by 16.8, which is going to give us, oh, sorry, hold on, I did this wrong. F net equals ma. Yep, there we go. F net equals ma. I'm looking for acceleration, my mistake. So then when I rearrange this, I'm going to get F net is already 16.8, which will
Federal
equal the mass
regulations
of
allow one
5
carry-on bag plus
times
one
the
small
acceleration.
personal item, such as a purse, computer bag, or briefcase. To maximize storage space for all customers, please put one item under the seat in front of you.
Now,
Carry-on items must not exceed the size check dimensions as shown near the boarding door. If it does not
acceleration
fit, please see a representative for assistance.
is going to equal 16.8 divided by 5, which will give us 3.35 meters per second squared. All right. So hopefully this is now making some sense for some of you who may have missed this lesson, and hopefully you can start applying some of this work. I will try to do some more lessons later on. Thank you very much. We'll talk to you later.